everyone. Good morning. Did you have a good sleep? I certainly didn't. I'm trying to survive with my 1 cup of coffee. Good morning. So it's day 3 of CESM tutorial. We're almost halfway through. I hope you're learning a lot. I'm just going to go through today's logistics. For the agenda, we have a ocean day. So in the morning, we will have 2 lectures on overview of ocean model and parameterization. And in the afternoon, we'll have biogeochemistry in the ocean. And then for the lab session today, we will have a Namelist and code changes, which is, I think, one of the more complicated labs. But this one is really fun because you can really dig deeper about customize your own CESM run. So this one is very useful. It's my personal favorite. Oh, everyone, every day is my favorite. I have to say that. Yes, so this is the lab outline. So the name list modification is from here. We're going to go through this and also troubleshooting runtime errors and source modifications. So these 3 chunks. The source modification will involve a little bit Fortran, but just a little bit, so don't worry about it. Yeah, so that's the outline of the agenda today. And then there is a very special event today happening at the Mesa Lab at 7 p.m. So Susan Solomon, who is one of the most distinguished climate scientists, is going to give a presentation about her new book. This new book is called Solvable: How We Healed the Earth and How We Can Do It Again. This event has been sold out. It's free, but the registration has already full, so we can't attend in person. But it will be live streamed, so you're welcome to attend. I don't know how it is organized in the dorm, but if possible, it can be, I don't know, a watch party or something like that. I don't know, it'll be fun with snacks and popcorn. Yes, so that's the event. I think we will send the link to maybe the Slack or the email, so you know where to get it. Cool. And yes, a little bit, speaking of Slack, we thank those who have added their information to the introduction channel. So if you go to the Slack and browse different channels, you will see there's one called introduction. We encourage you to write a little paragraph about yourself, your research area, where your institute is. Just introduce yourself to the participants. So from past year, we see that networking with your peers is very beneficial in the long run. I still keep in touch with my friend from CSM tutorial I attended in 2014, which is 11 years ago. Oh my God. Yes. And also, we will share a participant list on Friday, so everyone can know who participated in this tutorial for networking purposes. So if you don't want to share your information, you can ask Elizabeth to not include your name in that list. Yeah. So that's all the announcement I want to make. Make sure, yes. Yes, let's go into the first lecture of today, Ocean Modeling from Gustavo. I can find, yes.
Thank you.
Yeah, I think I'm going to put this on your...
Hi, good morning, everybody. Can you hear me fine? Yeah. My name is Gustavo Marques. I'm a scientist in the oceanography section here at CGD. I'm the co-chair and science liaison for the Ocean Model Working Group. So welcome to the first of 2 on ocean modeling classes. I'll teach the first one, and then Peter Gent here on my left will teach the second one. So the first one will be more like an intro, some basics, and then on the second one, we'll talk about the parameterizations, some of the key parameterizations that we use in the ocean model. However, before we start, we have 2 quizzes. Who here knows how much of the CO2 extra CO2 that's being put into the atmosphere since the Industrial Revolution is going where? Like, let's make it more broad. Where is that extra CO2 going in terms of percentage? Does anybody know how much is going in the ocean? Okay. 190%. CO2. That's for heat. So that was the second one. I'll give you points. So if the question would have been how much of the extra heat is going, over 90% is going into the ocean. For CO2, okay, close enough. So half stay in the atmosphere, a quarter goes to the land. That's because it's getting warmer and then there's more biomass growing, so the land is taking approximately a quarter of the CO2, and then the other quarter goes into the ocean. So from now on, every time you wake up, you don't go and check your phone right away. You thank the oceans for doing the job of getting the extra heat and quarter of the CO2. Okay, so now let's dive into how, like what we need to do from an ocean modeling perspective to represent those processes. That's what we are after overall, like how we need to be able to, excuse me, model that exchange and in a way that's consistent with the observations. So some general outline, so we'll be talking about some ocean modeling considerations, so the challenges for ocean modeling, some key ocean properties, then we'll dive into the equations, like very briefly, boundary conditions, and then horizontal and vertical discretization. Then I will talk about the two models that we're currently using here. So POP is the one that you guys are using for the practical exercise. So this is the last year that we are talking about POP. And then from now on, we'll be switching to the modular ocean model version 6 or MOM 6. But today, I will briefly talk about both of them. And then I'll end with some helpful resources. Okay, so the first order challenge for ocean modeling from a numerical perspective is that we have this highly irregular domain. So I'll play this movie from a high resolution MIT simulation. And you're looking at the surface currents, just to give you a sense, like how the land is exerting a control. So how you can see the coastlines controlling how the Gulf Stream behaves, like it goes between Cuba and Florida, and then you see the loop currents breaking and going towards the Gulf of Mexico. And then we see here now the North Brazil current, how it kind of goes against the coastline. Now we're going across the Atlantic. These are the so-called Agulhas rings. See how they're formed at the tip of Africa. So the coastline plays a huge role in how the ocean currents act. So just to give you a sense, so that's the very first order challenge. Like because of these irregular boundaries, unlike in the atmosphere where you don't have, like you have at the bottom the topography, the mountains, but in the ocean we have these sideways barriers that the flow needs to go through, and those play a key role in the setting up the currents. Okay, now let's talk about spatial and temporal scales. So on this plot, on the x-axis, we have the spatial scale going from 1 millimeter, so like molecular processes, all the way to very large, like 10 to the 5th kilometers, which is like things like, size of climate change and basin scale processes. And then on the y-axis, we have a time scale. It goes from 0.1 seconds, again, like molecular processes, to 10,000 years, which again, that's the time scale for climate change. And then you have a bunch of processes in between, going from things that are very small and fast, to things that are very large and slow. And if you were to highlight where our low resolution model, which is a 3-degree horizontal resolution version, would fall into, that's this green box. So our lowest resolution model that we have here is with CSM 3-degree. You can represent these large-scale processes like climate change, you get some El Nino, base scale-wise variability, seasonal cycle. Now, if we add the workhorse, so that's the model you guys are using in the practical lectures, which is a 1-degree, that's the black box. So now we go a little bit to the left, and we can start to get a little bit of the eddies, like at the equator where they're big, but no, very little. Some of the Rossby waves. Now, this is the highest resolution that we have today, which is a 1/10 of a degree. That's the red box. And now we go like almost everywhere we can get eddies. There's still a big region that we don't capture the mesoscale eddies in fronts, but now you get some things like coastal upwelling. Okay, so now let's do this. So the bottom line on this is that most of the ocean models used for climate applications, they represent the climate. They don't represent the mesoscale eddies. If you do an analogy with the atmosphere, so here's the same type of plot, time versus length scale. And now we plot the workhorse atmospheric model 1 degree. So right away, you capture most of the tropical cyclone activity right away. So the bottom line is that most of the global atmospheric models used in climate models, they simulate the weather. So it's a big difference. And we'll see why. Why a 1 degree model in one case represents climate change and climate processes, and the other one represents weather. Okay, so because of that, will be the second challenge in ocean modeling that we have. Because of the size of the spatial scales, they're smaller in the ocean, so it's much harder to represent them with the discrete equations that we use. So using the resolutions that we typically use. So on the left, you have a 1/10 of a degree. That's the model I talked before. And then on the right is the workhorse 1 degree. So this is sea surface temperature on 30th of September in 2000, in both cases. So you can see that the overall structures look similar. You get warm, cold at the bottom and warmer towards the north. You see this warm water coming from the east side of Africa. But then on the left, you see all these little structures. So those are the mesoscale eddies. There's Agula rings that we saw in the animation before. And they are represented on the left, but they are not on the right. So what we need to do is we need to be able to represent the effect of these eddies in a low resolution model like the one you see on the right. So that's a huge part of the business that we do. And on the second lecture, Peter Gent will talk more into how we do this. So bottom line, the mixing associated with subgrid scale turbulent processes must be parameterized somehow. Okay, now how do we estimate the eddy resolving scales? So to do that, we need to account for the density change from the top of the ocean to the bottom, and the same way that as we do in the atmosphere. And that there is a parameter that we call the so-called Rossby radius of deformation. So this first baroclinic Rossby radius of deformation, and that's this RG parameter. So N is the vertical stratification frequency, and H is the total water column depth, and then just this pi factor and divided by F. F is the Coriolis parameter. So in the ocean, the Rossby radius of deformation varies between 100 to tens of kilometers. So it's very larger because it's divided by F. You go to the equator, F tends towards 0, so the Rossby radius becomes bigger. So it's like hundreds of kilometers in the equator and gets towards 10 kilometers-ish, around 60 north and south. So two things, the Coriolis parameter and then the vertical stratification are the factors controlling this. Of course, the depth as well is playing here. So this map shows how much grid points you need in order to represent the first baroclinic radius of deformation. So for example, on the far left of the color bar is like a 1 degree model. So with the 1 degree model, the one that we have in the workhorse configuration, you can resolve some of the processes some of the mesoscale processes in the equator. If you go on the other hand, 1/10, so that will be around the yellowish, you can resolve up to the 60 degrees north and south, a little more in the northern hemisphere. You can go further high in the northern hemisphere. Also notice that as you go towards the coast, the Rossby radius of deformation increases. That's because H, the total depth, decreases. Okay, so now let's talk about equilibration timescale. In the ocean interior, once the water masses are formed and they sink, and I'll have schematic in a second, there's very little mixing that occurs. And because of this, we can name and trace these water masses. So therefore, there's very little mixing happening, and the time that it takes to adjust for an equilibrium, once you change the system, how long it takes for equilibrium to be reached, it's very, very large. And you can compute that by giving the total depth, h, squared divided by a typical vertical diffusivity, 2 times 10 to the minus 5, that gives you 20,000 years. That's roughly how long it takes for the deep ocean to equilibrate in terms of tracers or heat, fresh water. On the other hand, if you look at the dynamical adjustment, for example, the phase speed of non-dispersive long Rossby waves, let's take, for example, in the Pacific, around like 20 degrees south. So the dispersion relation, the CR, is given by minus beta. Beta is the change of the Coriolis parameter as a function of latitude times the radius of deformation square. So if you do that numbers, if you play with the numbers, it gives you approximately 750 days, which is 2 years. So 20,000 years on the top for the tracers to adjust in terms of mixing, and then dynamical adjustment, 2 years, much faster. So we need to be able to represent these two things changing. The one on the bottom is much easier, like 2 years fast. Like the one on the top, like you need to integrate the model, let's say for 20 years if you want to reach equilibrium at depth. And this is a schematic of how mixing occurs in the ocean as a function due to mesoscale eddies mostly. So the blue arrows are the mixing done by mesoscale eddies, and the red arrows are the mixing done by vertical mixing processes. And then the gray contours represent lines of constant density. So thank you. So the blue line follows isopycnals, while the red lines is across isopycnals. And then like in the ocean interior, most of the mixing, as I said, occurs along isopycnals. The effect of the red arrow is very, very small. And then you have this transition layer, and then near the surface, because there's a lot of mixing, we have the winds, the waves, then things are more homogeneous. So you see the isopycnals, they become parallel, and they become perpendicular to the surface. So the mesoscale eddies in that case, they are diabatic. They're crossing, making the properties cross isopycnals. So we need to represent, the ocean models need to be able to represent this schematic. So near the surface, you mix across isopycnals, and then in the ocean interior, you mix along isopycnals. That's very, very difficult. Just like from a discretization point of view, like your advection operator that has nothing to do with the mesoscale parameterization per se, all numerical schemes have errors. And an error in your advection scheme that leads to mixing across isopycnal is a big deal in the ocean model, because now you're creating mixing in the ocean interior, therefore you're going to have a very large drift, which is what we try to avoid. As I said before, you can name the water masses because of this very small mixing that occurs at depth. So you have the North Atlantic deep water, you have Antarctica bottom water, you have the upper circumpolar deep water, and so on and so forth. Okay, so now the bottom line for climate studies is performing long climate scale simulations at area resolving or even permitting resolution is not practical. Nowadays, computers are getting faster, and we are able to do longer integrations with high resolution models, but nothing close to thousands of years. So we must live with the deep ocean not being at equilibrium in most of the simulations that we do. Spurious mixing in the ocean interior can significantly degrade the solution. So that's this business I just talked about of you have to do mixing along isopycnals in the ocean interior. I didn't talk specifically, but we all know that the heat capacity of water is much larger than of air, and that's why the ocean is an important heat reservoir. It can absorb way more heat than the atmosphere. We talked about the quiz in the beginning, so over 90% of the excess heat is being stored in the ocean. And therefore, the ocean contains the memory of the climate system, and this is very important for long-term prediction studies. And there's many scientists here that are working on predictions, and hopefully that will be some of the specific talks that you see on how that's done. Okay, so now let's talk about the equations that are used to solve ocean models. So we have 7 equations and 7 unknowns. We have 3 velocity components, u, v, and w. We have equation for potential temperature, equation for density, equation for pressure, equation for salinity, plus if you have an ideal, like extra tracers, like CFCs, ideal age, there's 1 extra equation for each of them. And the passive tracers equation look just like the salinity and potential temperature equations, but they don't feed back into the dynamics like temperature and salinity do via the density equation. And we also make some approximations and scaling considerations. So the first approximation is the hydrostatic balance. So when the ocean becomes statically unstable, so when you have overturning, like you have a dense water going down the hill and that dense water like starts to form these Kelvin-Helmholtz instabilities, we don't allow that to happen with the hydrostatic approximation because the largest acceleration that's allowed is gravity, and the vertical acceleration, I should say. So then, you cannot explicitly capture these Kelvin-Helmholtz type of instabilities with the hydrostatic approximation. Instead, that needs to be parametrized via a vertical diffusion. So that is another type of subgrid scale process that is not included. It must be parametrized. We also make the Bose-Naski approximation, where we assume that the density, these changes in density in the ocean are very small compared to the mean density. Therefore, we can say that because of, like we say, rho equal rho naught plus rho prime, that's how you break that down, and then you say rho prime is much smaller than rho naught. Therefore, we can just, every time there's the density in the equation, we substitute by rho naught, with the exception of the continuity equation, where we continue to use actual rho. So the other assumption is the continuity equation, where we assume that the flow is incompressible, so we cannot deform the seawater, so what flows into a control volume must leave that control volume. The other one is the thin shell. So the ocean depth can be neglected compared to the Earth radius. So the way you can visualize the ocean is with a piece of paper, just get your book and like a thin piece of paper. That's how the scales in the ocean are compared. So you have very large horizontal scales and very small vertical scales. So the size of the basin compared to the depth of the basin. So that's the thin shell approximation. So together with horizontal motions being much larger than the vertical motions, there's the traditional approximation or the thin shell approximation, and with the Coriolis force results mean that in the Coriolis force, we retain only the horizontal components of the Coriolis parameter. We don't retain the vertical ones. Okay, now number 5, spherical Earth. So geopotential surfaces are assumed to be spheres. And then turbulent closure. So this is what I talked before. So all the subscale processes must be parametrized using the resolved large-scale features. So this is what I talked about, the mesoscale eddies, what I talked about, the Kelvin-Helmholtz instabilities for convection. Okay, so I'm not going to go into the details. This is a short lecture, only 30 minutes. This is the horizontal momentum equation in Cartesian form. Then you have the vertical momentum or hydrostatic equation. Then you have mass dash continuity equation. Then you have an equation for the transport of potential temperature. The same for salinity. Then the equation of state, which is a nonlinear equation, a function of temperature, salinity, and pressure. Okay, so those are the 7 equations. What are the boundary conditions? At the surface, we can exchange properties, momentum tracers with other components. In POP, there is no freshwater flux. Instead, they use the so-called virtual salt flux. So like instead of exchanging water at the surface, they adjust the salinity of the ocean to represent what would have happened if you had either rain or evaporated. That's not true in MOM 6. We actually use the so-called natural boundary condition where you add and remove fresh water. At the ocean bottom, you have no tracer flux, with the exception of geothermal heating in MOM 6. So MOM 6 has the option to force the model with heating at the bottom. The normal velocity is 0, and we use a quadratic bottom drag, which is the bottom boundary condition in the viscosity term. Okay, and then at the lateral, we have no tracer fluxes lateral, and there's the flow normal to a solid boundary must be 0, and there is no slip at the lateral boundaries. All right, so now moving to the horizontal grids that we used in these 2 models, starting with the so-called Arakawa big grid. In the Arakawa big grid, shown in this schematic, you have tracers being represented at the center of the grid, so capital T, that's where your tracers reside. And then at the corners, that's where U and V, the velocity components, are. So they're collocated, they're not on the same point, and then U and V are on the same point, and then tracers are on the center. And there's some advantages in using this type of discretization. First, it naturally fits the so-called no-slip boundary condition because you have both U and V on the corners. Also, it gives you a better representation of the Rossby waves when you use a coarse resolution model. So like if you use something like 1 degree or coarser, 2 degree, the B grid tends to give you better dispersion representation of the Rossby waves. And then finally, you have smaller truncations in the errors of the computation of Coriolis terms. Those are some numerical considerations just to keep in mind. So Arakawa big grid has some advantages. The disadvantage is that you cannot represent single point channels. So in the bottom right schematic, the blue cells are ocean and the green cells are land. And you have a channel where you have 2 ocean cells next to each other. And with a model with a B grid, you can represent, in that case, the flow going through that channel. So you need at least 2. If you had only 1 ocean cell between these land points, you would not be able to represent the flow going through because all your velocity points would be in the corner, so neighboring the land. So that is a disadvantage. Like you always have to make sure you have 2 points between channels. So with the low resolution model, that's very hard. It's a lot of manual tweaking of your model. Also, you have larger truncation errors in the pressure gradient terms with the so-called Arakawa big grid. Again, this is the grid staggering using POP2. The other grid is the Arakawa C grid. In that grid, the tracers are again at the cell centers, but now U and V are not on the same point. So U, it's on the same Y location as the tracer, but different X position. So they're staggered that way. And then V is the same, but like same on the X location and different Y positions. So now they're all on different points, U, V, and tracers. And then the Q points are where you have the vorticity points. So the advantage is right away is it allows you for a single point channel. So that schematic before, if you had only 1 channel with a C grid, you can represent the flow going through because now the V velocity will be active while the U velocity will be lambda. The disadvantages are the Coriolis acceleration terms require horizontal averaging because now U and V are not on the same point. So in order to compute velocity, you have to average them. And it makes the computation of internal gravity waves less accurate. And then you have poor dispersion relation for Rossby waves at very coarse resolution compared to the big grid. So if you were to design a model that only be used for low resolution, 2 degree, let's say, it makes more sense to use the big grid for numerical purposes, better representation of process. However, you're going to have to do a lot of manual digging to get these 2-point wide channels, which is very, very time consuming. Again, C-grid is used in MOM6. Okay. In terms of the vertical coordinate system in ocean models, so this is, together with the horizontal grid, the vertical grid is one of the most important choices one can make when designing an ocean model. And there's 3 main vertical coordinate systems in use. The so-called Z-coordinates on the left, that's what's used in POP. So in that system, the vertical spacing does not change as a function of your horizontal position. So if you go North Pole, in the Arctic, the first delta Z will be the same as the first delta Z in the Southern Ocean, for example. The second one in the middle is the so-called sigma or terrain following coordinate. In that one, your delta Z's are following the topography. So you have good representation of the flow near topography. And that become less so as you go towards the ocean, towards the surface rather. And then the further on the right is the so-called isopycnal coordinate. So in that one, you have your vertical discretization is given by the target densities. So you provide, let's say, 5 target densities, and then that's what the lines represent, so isopycnals, and then the delta Z's are varying as a function of position and your water masses. Okay, so going from the left is less complex, going to the right, it becomes more complex. And in the middle here, you have something in between. Each of them have advantages. So we like the Z model near the surface because you can have high resolution near the surface where you have a lot of processes exchange with other components. It's nice to have terrain falling near the bottom to represent bottom boundary processes. It's nice to have isopycnal in the interior because you need less mixing. You should be doing mixing along isopycnals anyway. So we like a little bit of all of them. That's why people have come up with this hybrid approach where you combine some of them and sometimes even all of them. So in MOM6, we use a hybrid coordinate where it's a combination of Z star with isopycnal on the right. And this is an area of active research, like how you do that, how you design your grid, how you choose your isopycnals, your delta Z's. So if you're interested, I'll be happy to talk to you offline. This is an area that we are constantly researching about. Okay, so I said MOM6 uses hybrids. That's the coordinate on the bottom. The very latest one is slightly different, but it's close enough. So you have near the surface, Z spacing, and then as you go around like 100 meters or deeper, we're looking at temperature near between 30 and 30 north and south across somewhere in the Pacific. So you transition from Z to isopycnal around 100 meters-ish. And you can see in the interior, the density here is mostly controlled by temperature, so the black lines, the isopycnals, follow the temperature gradients. We also have the option to do Z star in MOM, and that will be the one on the top. And then on the right, this is the grid that you guys are using with POP. So it's 60, in CSM1 was 60 level, I believe in CSM2 is 65. But this is just the vertical profile of the grid, so those are the delta Z's. You tend to have very small delta Z's near the surface, around 10 meters or so. And then as you go towards the bottom, like deeper than 3,000 meters, the delta Z's become 250 meters. Okay, so surface forcing options in CSM. So fully coupled mode, all the components are talking to each other freely, so there's no need to to prescribe any forcing. Everything is being done dynamically and prognostically by the components. But we also tend to run ocean-only simulations. It can either be the so-called C-comp set, that ocean is the only active component, or more often we do the so-called G-comp set, where you have ocean and sea ice active being forced by a data-driven atmosphere. And then this data-driven atmosphere, we use some of the protocols given here. So the first one is the so-called CORE protocol, is the Coordinated Ocean Ice Reference Experiment. So this was the first one that was put together. And there is two options. There is the interannual forcing at the top, and then there's also the normal year forcing, where you just keep repeating the same year. And then more recently, which is getting outdated already, is the GRA 55 forcing, which is kind of an updated of the core forcing. The GRA 55 is coming to an end. I think it was last year was the last year that they extended the forcing. So we here at NCAR, in conjunction with other labs, are putting together a new forcing protocol. Okay, so how much time do I have? -1. Okay, I will be quick. So POP is a Z-level model, as I said before. It was primarily developed at Los Alamos by the scientists there, and then in conjunction with scientists from NCAR. Is a three-dimensional model with the hydrostatic and Bose-Einstein approximation. We use a linearized implicit free surface formulation for the barotropic equation and the surface pressure. And then, as I said before, it uses the so-called virtual salt flux. Okay, so this is one of the grids that you were using, so that's GX1. G stands for Greenland. That means that the actual pole, the singularity point, was moved to Greenland, as you can see in the schematic. So we moved that singularity point to Greenland, and then X is the resolution to 1 degree. So that's a 1 degree Greenland displaced grid. That's the grid you guys are using. And notice that we have equatorial refinement. So we say 1 degree is actually nominal 1 degree because it can be higher near the equator. Okay. We also have tripolar grids for POP. That's the 1/10 degree. So now there's 2 poles on the northern hemisphere and then a pole in the southern hemisphere. And the poles in the northern hemisphere are put on land. Okay, now moving to MOM6. So now it's a finite volume solver. It has the option to do, it solves the hydrostatic, either Bose-Einstein or non-Bose-Einstein equations. And you want to use non-Bose-Einstein equations if you're concerned about sea level rise and if you don't want to do the correction offline. So MOM6 has the option to do that. Importantly, use the so-called arbitrary Lagrangian Eulerian approach for the vertical regridding and remapping. And with that approach, you can design any vertical coordinate system that you want. It can be a terrain following coordinate, a z coordinate, an isopycnal coordinate, or a combination of all of them. And because you do this regridding and remapping, there is no vertical velocity. Therefore, there is no vertical CFL. Instead, the vertical velocity is represented when you remap to a target grid. That means you can do ultra-fine resolution at the vertical. It has subcycle gravity waves and built-in wetting and drying. So you can do things like ice shelf retreat, and then the ground line of shelf moving and the ocean going into and out of dry cells. Okay, there's a bunch of parameterizations in general in MOM6. So those are the mesoscale, and we continue adding. This is a non-ending list. Surface boundary layer schemes. We have 2 sub-mesoscale processes: shear mixing, shortwave penetration, bottom boundary layer, geothermal, internal type-driven mixing. So there's a whole zoo of parameterizations available in MOM6. Because it's a community model, it's an open source development, there's multiple institutions using, so it's constantly being updated and developed. Okay, some helpful resources. This is for POP. If you're interested, I'll let you go through afterwards, and you can find all these things, post-processing, the documentation. And then there's the POP forum here that we maintain. And then the same for MOM6. There's a web page for getting started, some lectures, the webinar series that we had in 2020. then read the docs, then there's stuff for post-processing tools, and finally the MOM6 forum. Okay, some references, and I'm happy to take any questions. Thank you for your time.
Hybrid approach for the vertical coordinates in MOM versus POP. Like in POP, we stick with the Z coordinates at the surface.
Yeah.
How would having that hybrid approach to do like isopycnal below the surface, like around 100 meters, change like surface
Great question.
values, like hydrological processes? Would that be better there too, like that how those talk to each other?
Great question. So in POP, you always have system throughout the whole water column, Z, right? So in order to represent this, right, so like a long isopycnal, you need to rotate your velocity tensor. So we do, it's very computationally expensive. Like when you're in a point, then you need to find what is the slope of your isopycnal. Then when you apply your transport, you need to rotate to be parallel to the isopycnal. So we do this rotation using the velocity components and tensor stress and so on and so forth. That's and it's prone to error. It's not. It works well, but there's a whole set of people that came up with these methods 15, 20 years ago. So that's how you would do it. You would rotate your advection direction.
So is MOM, like, would you say that MOM is going to be better at kind of simulating those like advection processes and get better like salinity values at the surface?
Oh, at the surface.
Like coming up from it, would that happen?
Right. So we're talking about ocean interior. That's when the low isopycnal matters. At the surface, things are more parallel to the ocean surface. So across isopycnal, you have a lot of across isopycnal mixing.
Okay.
So even in MOM, when we represent the diffusion due to mesoscale eddies, for example, as we go near the surface, we do that horizontally rather than along isopycnal.
Oh, okay.
In the interior, we do along isopycnal.
Okay. Okay, thank you.
But you're right. It will be presumably the appealing. One of the appealing parts of MOM6 is that it will give you less spurious mixing. That's the technical word that we call it.
Yeah, thanks for your talk. I have a question regarding the atmospheric forcing. What about ERA 5?
Yeah, so ERA 5 is being used to generate those forces. My understanding is that by itself, it's not enough. It does not have enough fluxes to force the ocean model in a precise way. So these protocols, I know the new one that we are developing is based on ERA 5. So we get ERA 5, we do some correction on top of ERA 5, then add what's missing, and that's what the protocol will be. So again, I can follow up with you later, but my understanding is that ERA 5 by itself is not enough to be used as the reference, the forcing protocol.
What was the reason for the decision to switch to MOM6 rather than develop POP?
Yeah, as I mentioned, POP was primarily developed at Los Alamos National Lab, and then the people that were developing was retiring or no longer in the field, and then kind of we lost critical mass for developing the model. It was pretty outdated already, and then the Ocean Model Working Group decided to switch to a new model. Then we opened up for all the existing models at the time, and there was a committee that was formed, and then MOM6 was chosen.
I had a more functional question about running the code. I was noticing that you said, for example, if you want to do ocean CI simulations, there's a GCOM set. Is it as simple as when we build a new case, you just specify the comp set and that's taken care of? Or
Correct.
do we need to do anything more involved?
No. So you just say G, JRA, and that will give you a GCOM set with GRA forcing. Yeah, it's very easy to use.
I have another question about that like vertical coordinate system. When you have a hybrid grid where you're transitioning from like the z coordinate to the isopycnal following, do you have to worry about potential like errors or weird stuff happening in that transition spot if there's like a hard cutoff transition, or is it somehow smooth or?
It's smooth, yeah.
Okay.
Yeah, so you can kind of see, so what happens is like thinking of the discretized equations, you're exchanging properties with your neighbor, right? If you're in a z coordinate, you'll potentially be doing things across isopycnal. And that's what the whole business I set off, like you need to rotate your operator if you want to be in a z along isopycnal. And then when you switch to density, your neighbor will be on the same density as you. Then like you're doing along isopycnal. So the transition is not a problem like that you go from one to another in terms, because you tend to keep those places in a location where you want to be Z star anyway. So you like if you're doing extra, like it's fine because you are in a location of vigorous mixing.
Okay, so that transition between the two grid types is like co-located with the actual transition region, like from the mixed layer. Is that kind of the idea?
Well, so mixed layer, like everything that involves isopycnal will be captured by your density part. So it's a whole art how you prescribe your density targets, and then that will conform to the water properties, right? The water properties in the ocean magnitude will be mapped to that. So I shouldn't say we know pretty well how to do this because it's very active area of research, and in order to do that properly everywhere, it's going to take us some time. Right.
So we mentioned earlier of applying like an effective salinity at the river mouths. So I was wondering if such an approximation would also affect like the ocean flows, like
You're talking about
velocity
virtual salt flux
Yeah.
in pop?
Yeah.
And then if that has effect on the flow?
Yeah, on the flow.
No, it's a robust way of representing if you imagine you have a bucket and you add a glass of water. So instead of adding the glass of water and making the bucket less salty, you remove salt from the bucket.
Yeah, I understand that part. I was just wondering, when river goes into like ocean, it has a velocity, right? So that kind of adds to the velocity field. I was
Right,
wondering.
so for that, there is a parameterization called the estuary box model.
Okay.
That is meant to represent the overturning caused by estuaries. For example, the river mouth, you have this estuary exchange where this process that you're talking about, the velocity exchange, so it's another parameterization that we add. It does use virtual salt flux as part of the parameterization.
So we kind of do both, right?
Yeah.
I see. Thank you.
Yeah, just a question. Do you have mesh refinement option? Like, how do you handle the coasts?
Yeah, we do now. So MOM uses the so-called curvilinear grid. So does POP. So we can do some refinement, as I show, for example, here. So this is for POP, but the same with MOM. There's an equatorial refinement. So we get grid size smaller as towards the equator, so we can resolve the processes better. So there's some freedom with the curvilinear grid system, not as much as like a unstructured grid that you can go from like a 1/10 of a degree to like a 1 degree within 1,000 kilometers. It's way more limited. There's someone in the building today from Turkey that is working on making a global grid with MOM6 that will be like a 112 in the Mediterranean, and then will be like 1 degree outside in the Atlantic. But it's the first time I'm seeing this. I think it's going to be very challenging. It was not meant to do the same as an structured grid, for example.
So, which type of data sets are being used as boundary condition?
Which type of variables?
Data set, like observational data set or reanalysis.
Yeah, so for, like when we do forced ocean, or like the C or G cases, you need the short wave, short wave, long wave, then you need to know the velocity in the atmosphere at the bottom level of the atmosphere, then we use, and temperature, and then we use the so-called bulk formula to compute the stresses, as well as the turbulent heat fluxes, sensible and latent. We also, in MOM, because it's a natural boundary condition, this precipitation, evaporation, runoff, and then there's the heat associated with those mass exchange as well. Yeah, so it's a pretty big list, but like just to give you a hint here.
Great timing. Okay, let's thank Gustavo.
So, compared to the last talk, this is going to be an old school talk from an old school guy. Old school guys sort of wander around in front of the audience. They don't stand behind, so we really annoy the guys in the back because they can't follow us with their cameras. But I'm going to talk about the two most important parameterizations in ocean models. And the first one is a vertical mixing scheme. And why is it so important? The ocean is different from the atmosphere. First of all, it's wet, but secondly, and most importantly, it's forced from above. It's forced at the surface by the winds, the heat fluxes, and the water fluxes that come in. The atmosphere is often forced from below. That's how you get convection, which we might get today, but we probably won't because it's going to be too hot and too dry. So the ocean is different. The only forcing that Gustavo mentioned that comes possibly from the bottom is a very small amount of thermal forcing from ocean vents. All the rest comes from the top. So what happens down below in the ocean is all caused by the vertical mixing scheme. So that's why it's so important. And we still use this vertical mixing scheme called KPP, K-profile parameterization. And it was first published in 1994 by a colleague of ours, Bill Large, Jim McWilliams, and Scott Doney. And it's still used today. It's very relevant still. So unresolved turbulent vertical mixing due to small-scale overturning motions is parameterized as a vertical diffusion. These old school guys have old school pointers. It's guided by a study of observations of the atmospheric boundary layer. So the time rate of change of a quantity x is minus d by dz of the average of the perturbation vertical velocity and the quantity x. And if you parameterize this flux as a minus kx d by dz of x, then what you get is a vertical diffusion of things going down. And kx represents an eddy diffusivity or an eddy viscosity, and the x's are either active or passive scalars and or momentum. Now, one of the new things that KPP did was it isn't just a vertical diffusion scheme, because the scalars, temperature and salinity, have a non-local or a counter-gradient effect, gamma x. By the way, this was put up specifically to stop me getting too close to the screen and touching it. Thanks, guys. So this was new. All the vertical schemes before that were just vertical diffusion. So this was a new scheme, and it had important consequences. So KPP involves three high-level steps. First, the determination of the boundary layer depth d. Second, calculation of the interior diffusivities, nu of x. And third, the evaluation of the boundary layer diffusivities, kappa x. Now, Diffusivity throughout the boundary layer, where the vertical mixing is really strong. This is where the wind forces the vertical mixing. Depends on the surface forcing, the boundary layer depth, and the interior diffusivity. And KPP produces quite large diffusivities below the boundary layer depth, which mixes temperature and salinity quite deep in times of very strong surface wind stress, such as strong mid-latitude atmosphere storms. And this property, due to this not countergradient term, was new, that you've got significant vertical exchanges below the depth of the boundary layer. This was a new aspect of the KPP scheme, which is important in improving representations of the upper ocean. So, most important, how do we determine the boundary layer depth? And it's determined by evaluating this bulk Richardson number, RIB. So what you do is you go down to layer 1 and determine what the value of the Richardson number is. If it's not small enough, you go down to the next layer, and then you calculate this Richardson number as a difference between the surface buoyancy, BR, and the buoyancy at that depth, D, divided by the square of the difference of the velocity between the surface and the velocity, horizontal velocity, at that depth, D. And we have this little extra term in there called unresolved shear, just in case these two are equal, and we don't want the Richardson number going to infinity, which blows up the model. So you go down at each level, determining the bulk Richardson number until it's small enough, less than this critical Richardson number of 0.3. And there, at that level, you determine that that is the boundary layer depth at that point. And the Richardson number measures the stability of stratified shear flow. So in traditional things in Kelvin-Helmholtz, you go down to a critical Richardson number of 1/4. And once you go below that, you get instability kicking in. In this case, with this bulk Richardson number, you go down till you find a level where the bulk Richardson number is below 0.3. So this measures the stability of stratified shear flow. And quote from this paper, boundary layer eddies with a mean velocity VR and a buoyancy BR should be able to penetrate to the bottom of the boundary layer depth D, where they first become stable relative to the local buoyancy and velocity. So you determine this boundary layer depth, and it's where the wind that's strongly forcing at the surface produces the turbulence, and that down to that boundary layer depth, you get very strong mixing of things getting taken down from the surface down to that level. Then, below that boundary layer depth, you have a little layer, a transition layer, where you can get quite large vertical mixing, and then you get into the deep ocean where there's very small vertical mixing. So it's that transition that's difficult to do, and this KPP scheme was the first one that did it better than just a pure diffusion. Once you get into the diffusivities below the boundary layer, then you get into the region of a small vertical mixing, and there's all sorts of things that can affect that vertical mixing. For instance, we're often asked, how do the tides, which are important in the ocean and a big signal, come in? And they can produce some tidal mixing below the boundary layer, where it's significant. There's things called internal waves, which are internal waves can break, also causing mixing. And we have something called unresolved shear instability. So down below the boundary layer, and in the ocean interior where there's small vertical mixing, there's a combination of things that produce that small vertical mixin. And then below the region where the wind is really the driving force. Down below, you've got other things that kick in. So, how did this new scheme do in comparing observations on the top here against the model? Now, those of you who don't know Bill Large, he's from Canada. So he got his degree at UBC. So the nearest place where they got observations was Ocean Station Papa, 50 degrees north, 145 west, which is off the coast of Vancouver Island, and it's still maintained out there as an ocean observing system. And you see what old guys do. We compared to observations in 1961 and 62. I was born then. Most of you probably weren't. So this is the observations here. In fact, all of you weren't born in 1962. So this is saying the observations. So the boundary layer depth is weak in the summer. You've got light winds, and you've got a lot of solar radiation coming in, so the boundary layer depth is not very deep, 20 or 30 meters. As the fall goes on, the solar heating gets weaker, and the winds get stronger. If you ever go out on a boat to Ocean Station Papa, then don't go in the fall or the winter, because the winds will be stronger and stronger. So the depth of the boundary layer increases through November to around 90 or 100 meters. So the boundary layer depth is smallest in the summer, largest in the winter. And this is what the KPP model did. Now, you can decide for yourself whether it's any good. But the guys in the paper reckon this was a pretty good simulation and better than what had been done before with a purely vertical diffusion scheme. So as I said, KPP has had a long lifetime. It's still used in many ocean models, and it has a rather impressive number of citations against its name. Now, need a little drink here. The other parameterization I'm going to talk about is my favorite. It was first proposed by myself and Jim McWilliams in 1990. And that paper is pretty difficult to read. But in 2010, I was asked to write a review, which I entitled 2020 Hindsight. If you want to read more about it, that's the paper to read. Now, as Gustavo nicely pointed out, here's a plot of a GFDL model that has a 1/10 of a degree horizontal resolution. So it, quote, resolves the mesoscale eddies. So all this sort of turbulence down here at small scales, and actually these are tropical instability waves off the coast of Central America, basically. This is the Galapagos Islands over here. So as Gustavo nicely pointed out, 1-degree models don't resolve these eddies. So the effects of these eddies have to be parameterized. Now, the next slide, I realized that he'd already shown. So did you steal it from me, or did I steal it? Yeah, you stole it from me. Yeah. So, again, there's a difference between what you can resolve with a 1/10 of a degree and what you can do at 1 degree. So at 1 degree, you have to parameterize the effects of these eddies. Now, the other thing he talked about was that the diffusion needs to be along isopycnal surfaces. And this is because in the ocean, observations tend to tell us that mixing along isopycnal surfaces is on the order of 10 to the 7th greater than the mixing across isopycnal surfaces. And as he pointed out, this very small mixing across isopycnal surfaces is the reason that you can name water masses and follow them through the ocean where they go once they're buried. So something like Mediterranean water. This comes over the sill at Gibraltar. It's very salty because there's a lot of evaporation in the Mediterranean. That water comes out at a large value of salinity, smaller values of temperature, and you can follow that water as it sinks slowly and goes across the Atlantic. And the reason that these old guys, oceanographers, could name these water masses and follow them by getting the T-star relations is because mixing across constant density isopycnal surfaces is so small in the ocean. It's very different than in the atmosphere. Now, early models were all Z models, mostly produced by GFDL MOM models. And to start with, they had the horizontal mixing was along the Z surfaces. So it was in this direction and not in the isopycnal direction. Given that the slopes of the isopycnals are 10 to the minus 3 or 10 to the minus 4, yet the difference between the mixing rates is 10 to the 7, that if you had mixing along these surfaces, you would imply too much cross-isopycnal mixing. And this was a problem in the early models. And George Veronis in 1975, so 50 years ago, pointed out that it produces spurious upwelling in the western boundary current regions, which short circuits the Atlantic meridional overturning circulation. I'm going to use this MOC a lot, meridional overturning circulation. And thus, there was a recognized need to orient tracer diffusion in Z-coordinate models along isopycnal surfaces in order to be consistent with those ocean mixing rates. That was done in the mid-1980s. But still, there were some slight problems with ocean models. So in 1990, Jim McWilliams and I proposed that the effects of eddies, as well as having this diffusion along isopycnal surfaces, that the eddies had an extra advection effect, U star. And we proposed a form for U star, which is related to the slopes of the isopycnals, grad rho over rho z. And it's implemented as an extra advection. And it was in addition to the diffusion along isopycnal surfaces. And this was a new proposal. There'd never been a proposal that the isopycnals, that the eddies would have an advective effect. So, where does it have its biggest effect? And the biggest effect is in the Southern Ocean. So this is a plot. Antarctica on the left, going north as we go right. And here you can see that they name these water masses. Antarctic bottom water, North Atlantic deep water, Antarctic intermediate water, and a whole bunch of others that I don't know what they stand for. Now, there's a zonal wind jet centered somewhere close to 50 south, which is blowing strongly out of the board towards you. And it produces in the ocean what's called the Antarctic Circumpolar Current. The Antarctic Circumpolar Current is the strongest current in the world's oceans. It's twice as strong in volume as the Gulf Stream. And it's the only current, as its name implies, which is circumpolar and goes around Antarctica. So you've got a strong current here and weaker currents on either side. Now, we're in the Southern Ocean, Southern Hemisphere, so Coriolis is pushing things to the left. So that push is strongest where the Antarctic Circumpolar Current is the strongest, and it's weaker on either side. So it produces a convergence here, and if water converges at the surface, it has to go down. It produces a divergence here, so water has to come up. So the mean flow is producing an overturning circulation. It's in this direction. It's clockwise. And what the effects of the eddies that are ubiquitous in the Antarctic Circumpolar Current is it tries to balance that effect of the mean flow by having a circulation in the opposite direction. So an anticyclonic circulation, anti-clockwise. So the mean MOC is producing a clockwise circulation here, balanced to some degree by a circulation in the opposite direction due to these eddies. And this was new because this is due to this extra advection. Now, the first time this was tried in an ocean model was done by a new postdoc we had named Gökhan Danabasoglu. And it was in a really coarse resolution model to start with, 4 degrees by 3 degrees by 20 levels. And we ran 2 cases. One where there was just horizontal diffusion, and the second one where the diffusion was along isopycnals and it had this extra advection. And these are the overturning circulations that came out of that model. Now, the overturning circulation, you've got du dx for dv dy plus dw dz is 0. If you average that in x, you get a circulation stream function, which tells you about meridional and vertical motions. So in this stream function, things are going clockwise around the positive contours, anti-clockwise around the negative contours. So here we've got water going down. And that is called the Atlantic Meridional Overturning Circulation, AMOC. That all happens in the Atlantic Ocean. You may have heard of AMOC. It's reasonably well known. Elsewhere, things are going the other directions. But here, in the ACC region, is this positive circulation due to the mean flow. Going down here and up on the southern flank of the ACC. And polewards of that, you've got a circulation which produces Antarctic bottom water up against the continent. Now, if you plot the same function in the case where we had isopycnal mixing and GM advection, this is what you get from the mean flow. It's similar, but for instance, it's stronger in these locations here, 12 sphere drops compared to 8. And that's because you've eliminated that Voronezh effect. You've also got much weaker and better, smaller amounts of formation of Antarctic bottom water. But you've still got this powerful overturning due to the mean flow. Then we plotted the overturning circulation due to the mean flow and the advection, the eddy advection. Northern hemispheres, there's not much difference. 16 Sverdrups over here, 16 over here. But look what's happened in the region of the ACC. You've gone from this really strong circulation here to almost no circulation there. So the overturning circulation due to the eddies is strongest in the region of the ACC, and in this calculation, it's almost balanced, the overturning due to the mean flow. These integrations, for example, were integrated to equilibrium. They were integrated for 10,000 years each. Now, what's the effect of this extra advection? Here, you're going this way, so you're transporting cold water at the surface farther north. So over here, you've got cold water above warm water. That is denser water above lighter water, and that is statically unstable. So you will mix that with a very strong vertical mixing coefficient, because in these ocean models, the hydrostatic approximation, you need to be stable with density decreasing as you go up in the vertical column. This also is taking cold water farther north. Ocean and the atmosphere need to be transporting heat polewards in both hemispheres. Heat's taken in more at the equator, and it's taken northward and southward to balance things near the poles. So this was a big surprise to us, that this overturning to the eddies was so strong and balancing the mean flow. And what did it do? As I pointed out, in the one with just horizontal diffusion, you have all sorts of, quote, deep water formation going on because you've transported that cold surface water above the light surface water. And if you asked an old-time oceanographer or observationist person, is this anything like reality? They would say no, because they knew that deep water formation in the ocean only occurs in a very few places. And once you put this GM and isopycnal mixing in, they go, all these things in the Southern Ocean go away. And the only places where you get deep water formed is in the Greenland, Iceland, Norwegian seas, called the Jin Seas, the Labrador Sea, the Weddell Sea, and the Ross Sea. And these are the places where observationalists knew that these are the locations where deep water is formed, where you get really statically unstable regions and the water goes down potentially several thousand meters. So if you ask this old-time oceanographer, real oceanographer, not a computational oceanographer, by the way, which of these would be better, they would absolutely say, this is right. And it was this simulation that encouraged us to couple this up in the first CSM run to an improved atmosphere, and I've forgotten my GM summary. Here we go. Mimics the effect of unresolved mesoscale eddies as the sum of diffusive mixing of traces along isopycnals and additional advection of traces by the eddy-induced velocity. That extra advection is an adiabatic scheme, so it's valid for the ocean interior. It gets absorbed with other things in the surface where there's so much more of the mixing going on. That advection acts to flatten the isopycnals and to reduce potential energy, which is what baroclinic instability does. It tends to flatten isopycnals, reduce potential energy. and it eliminates any need for horizontal diffusion in z-coordinate models. That run that we did was absolutely stable, so you don't need any horizontal diffusion at all. And implementation of GM in this ocean model was a major factor enabling stable coupled climate models to run without flux corrections. And what you need to remember is that this model started off as MOM1. We added KPP and this advection scheme, and we called it the NCAR CSM ocean model, NCOM. You need to remember that in 2 minutes' time. So, as I said, this CSM1, where we had this KPP and GM for the first time, was the first ever climate model run that produced a non-drifting control run without the use of flux adjustments. Always before that, the fluxes of heat and water that the atmosphere model wanted and the ocean model wanted were so different that if you wanted to maintain a stable climate, you implied at every time step these flux adjustments, which were the difference between what the atmosphere and the ocean wanted at every time step, in order to keep the climate model stable as you ran forward. This was basically a cheat. This was the first model wherever a stable temperature profile was maintained without the use of flux adjustments. And this is a plot showing that the temperature is only changing by a very, very minimal amount. It took 10 years to adjust, and then it was stable. Once these things were put into the ocean components of other climate models started to be able to run without flux adjustments. Now, in the year 2000, I was invited to give a talk on GM at a conference in Limerick, in Ireland. So what is Limerick known for? Guinness. Guinness. Even I drank a little Guinness over there. But the temptation was too great. So I wrote a limerick. Starts the first line. There once was an ocean model called MOM. This is how all the best limericks start. There once was something. So, there once was an ocean model called MOM, which occasionally used to bomb, but eddy advection and much less convection turned it into a stable NCOM. Thank you.
Peter, for an awesome talk. Questions for Peter? Simmering this limerick.
It was so well explained that there's no...
Yeah, question from the back.
I guess I have a question about just how did you, formulate the GM parameterization? So you showed the formulation as a function of density, essentially. And I guess this is an exercise in learning how do you do these kind of things. So what was that journey? How did you get to that? Was it a theoretical formulation?
So that's formulation. If you look at the potential energy quantity for, and its dBdt of potential energy, that term with the extra advection comes in. And if you evaluate it with the slope of the density surfaces that you get, the term in the potential energy equation is a definite sink of potential energy when you globally average it in the ocean model. And that's what we wanted, because that mimics the effects of baroclinic instability, which is to flatten the isopycnals and to reduce potential energy. And that particular form we chose because it did that if you do that equation for the potential energy. And that's in that 2011 paper. So were we lucky? I don't know. Were we brilliant? You guys decide. You guys decide.
Yeah, question there first, yeah.
Yeah, so from what I understood, like, so the eddy impacts are mainly over the ACC region.
Yeah.
So to understand AMOC, do we have to consider eddy or is just the mean eddy, mean AMOC is enough?
So those overturning circulations in the ACC are on the order of 12 or so spherups. If you look at the overturning circulation due to the eddies in the North Atlantic, it's 1, possibly 2 spherups at most. So to first order, the contribution of those eddies, the extra advection by those eddies is very small in AMOC. So to first order, you only have to deal with the mean flow when you're talking about AMOC stability. In terms of AMOC, there's been much publication about is AMOC going to decline as we go forward. And I'm personally not very happy with most of the publicity that comes from AMOC because they always show AMOC is a tipping point, that will it stop if we go past some things? And there are papers being written using our CSM models saying we're going to have a AMOC collapse. Some say in just a few years, some say in the 2030s. But I have never been convinced very much by the papers that have been written on that. And unfortunately, there are certain individuals that love this publicity, and as soon as some paper comes out saying there's a possibility AMOC might reduce, all the reporters go to these same individuals who've made their careers by saying tipping points in AMOC. So personally, I don't see I'm going to live to a time when AMOC collapses. You guys might live to a time when AMOC collapses, but not me. Yes.
In the atmosphere where the synoptic and planetary eddy advection is well resolved, it's pretty straightforward to compute the eddy-induced circulation and transformed Eulerian mean using monthly Eulerian diagnostics, as long as you output the eddy covariances. But I'm wondering, with the eddy advection parameterized in the ocean, is it equally straightforward to compute the eddy-induced advection diagnostically?
Yes, because you just use that formula that's in there. And when people run these 1/10 of a degree, quote, eddy resolving simulations, GM is not used because, quote, the eddies are resolved, so you don't need this parameterization. They still use that thing about any mixing in the deeper ocean goes along the isopycnals, because you will still get into trouble if you don't respect the isopycnals in the deep ocean. But there's analogies that I've written a paper about between the effects of eddies in the ACC and in the atmosphere. Because it's circumpolar, if you look at the zonal momentum equation, you've got a minus dp dx there. If you integrate round, that term goes away. So there's a completely different dynamics between a circumpolar current in a mid-latitude. If you integrate across the Atlantic, PDX is a big term. So there's a big difference in dynamics. So the dynamics of the ACC is much more similar to atmosphere, and there's a non-acceleration theorem by McIntyre and others, which sort of applies in the ocean. So, yes.
So this original, I guess, validation paper you integrated for 10,000 years and until it's as a stable climate. And the current outlook is that the zonal wind stress has been increasing in the transient climate. And this would accelerate the ACC. And there's a lot of literature on eddy compensation.
That's right.
But these are using these high-resolution models with increased topography. Topography can excite its own variability. And so in your smoother 3x4 degree model, there's not really a lot of topographic effects that can be involved.
Right.
So in your opinion, how much of, and there's a lot of literature on changing your coefficient and making it spatially variable to get this eddy compensation. But even in these ripple eddy emitting models, you don't have full compensation necessarily, it's usually partial. So in your opinion, is the partial or even full eddy compensation solely due to a transient baric mesoscale eddy, or is the topography also very important?
So that's, he knows too much. Yeah, not a lot, but he knows too much. So we've observed over the last 20 or 30 years that jet in the Southern Ocean is A, increasing, and B, moving very slightly to the south. So that induces a stronger ACC, more mean flow overturning, and a greater eddy variability because the winds are stronger. So the question is, does the eddy compensation completely balance that due to the mean flow, which it did in my thing there? And the answer is that most high-resolution models say no. And in fact, most even non-eddy resolving models, that the eddy compensation against the mean flow is not as complete as in that one that I showed. So the bottom line is that the eddy compensation is normally very significant, but is not complete. And then there's questions about, is it just a transient eddies or is it stationary eddies as the flow comes around the south part of South America through Drake Passage? It then has this big northward tilt, and there's sort of topographically forced deviations. And it's still a question. The Australians always debate are you Australian?
No.
Oh, okay. That's good. But there's a lot of literature, and there's some summary in a review I wrote about what's the effects of increasing southern hemisphere winds on ocean models, where I go from non-eddy resolving through to eddy resolving. This that was in somewhere you can look up. It's how many years old now? 8 or 9. So there's a lot more literature. But that was the state in 16, is it? Yes. I think he knows far too much. Question over here.
I have a much different question. I just looked at you a little bit. I'm a big bird guy, and I noticed that you are also into birds in the Colorado area. I'm familiar with like Texas birds, but you're familiar with Colorado birds. So as a bird watcher visiting Colorado, what should I look for?
So, I've spent, since I came to Boulder in 1976, I've spent much of my time bird watching. And I've seen a lot of birds in Boulder County, the state. Unfortunately, I've had trips, many trips elsewhere. At the moment, there's an extremely rare bird in Boulder County called an anhinga, which is a tropical species, which is a bit like a cormorant, if you know what it is. It's common in the tropics, and in the US, most of the population is in Florida. And it has a very sharp bill, so it catches fish underwater by spearing them, rather than catching them in its mouth. and it comes up, and often it just has its neck and head out of the water, so it's called a snake bird. And I've seen it come up, flip the fish off its bill, and catch it. And there's been one in eastern Boulder County since June the 2nd. And it's been seen by more people than any other rare bird ever in Colorado. The number of people who've seen it now is like 800 or 900, it could even be 1,000. Because there was some publicity. It was A, in the Denver Post, and B, on Channel 9, where you could see me in a different red t-shirt, the Colorado field ornithologist. And that was unique because it was only the 4th record of anhinga ever in Colorado. The first 2 were collected, shot, in 1927 and 1931. The 3rd one was briefly observed at Bar Lake, which is northeast of Denver, in 2003. So this was the first observation in 22 years, and me, as a keen bird watcher, got all excited about going to see it, because as a keen bird watcher, I keep a list of A, the birds I've seen in Boulder County, and B, the list of the birds I've seen in Colorado. So, there we go.
Yeah, following up the bird, my PhD is about climate and bird migration, like the chapter.
Oh,
So
you're a wonderful person.
tropical Indian Ocean and Pacific Oceans impacting bird migration in North American boreal forest and Appalachian region, right? And we also have a bird like impacted by the Southern California and Baja regions of ocean. So I wonder, did you like look into the ocean circulations and stuff like that's how impacted the atmosphere circulation, that remotely the kind of connection between ocean? And I use CESM for understanding these patterns. So sea surface temperature, boundary forcings for understand circulation that impacting birds.
Yeah, I'm not so up on the seabirds, but in terms of land birds, of the last 25 species which have been added to the Colorado state list, probably 75 to 80% of them have come from the south. So climate change is affecting these bird distributions by things from the south getting more and more comfortable as they come north. There's also been many studies about as warming meant that these birds come earlier in the spring. There's so much variability in Colorado's weather and in the spring that I have personally not seen very much change in the arrival times of birds in the spring. So there's been more of that in Europe. But it's definitely true that as the temperatures have warmed, bird migrations have changed. The other thing that's happened is, as the winter temperatures have warmed, especially in southern Colorado, more and more species hang on before actually going south. A thing like cormorants or birds that feed in the water, it's got later and later before the reservoirs here freeze over. So more and more of those species are staying through parts of December before having been forced to go south when they freeze over. And personal observation is that winters have got milder since I've been here, which is okay. But the summers are getting harder, which isn't okay. So it's been, all right.
Okay,
Thanks very much.
Peter again.
Okay, welcome back then. You are on your way to become expert of CSM, and today we are going to dig to the next step that we are going to do Namelist modification, then what to do when the model crash, and then we will go even one step further, code modification. And here I want to remind here, I'm only here to show the door. I can talk about CSM for this. I just run this like from over 25 years. But I think you have really to learn yourself how to do it, and you have to do mistakes. Sometimes it's very frustrating, but it's where you learn the most. It's when nothing is working. And it's good that when nothing works, when you are here, because you have people to help. When you are alone in your office, it's more difficult. Then I'm going to keep it short, because I think you learn better on your own. It's a self-paced exercise, then call for help when you need. But I'm going to just give you the overview what we are going to do. Then the first thing that we are going to do is the name list modification. Then in your book, it's over there. Then what we are going to cover today. And you will learn first what are the name lists and how to modify them. Then first, before doing the exercise, read the documentation about the name list. And name lists are files that I use at runtime when the model is running. And for instance, you will see that how to change the output frequency of the model. By default, the model outputs monthly data. But let's say that you want to look at the daily cycle. It's not that useful. Then you want to change the frequency of the data. Then we are going to have an exercise how to do this. And a disclaimer, I'm doing mainly the atmosphere model, even that I do a lot of the couple. Then a lot of the examples that I pick are coming from the atmosphere, but what you learn, it's transferable also to other components. But the exercises themselves are more about the atmosphere. Then you will have here in the name list modification. Then on the plot here, I'm showing where you have to modify the name list. Then you will have to modify the name list inside the case directory. But the name lists themselves will appear in two places. I'm going fast here, but you will read this on your own. But they will appear over here and over in your run directory and in your case directory in the form that the model component _in, and you should not modify this. You should really modify the file here. This is small here. You will see this in the documentation. Then the second thing that you will do is that your model crash, what do you have to do? And this is taken from the web. It's not my husband, this one. But what do you have to do? And we're going to do a fun exercise here. Then you will learn to look at log file. Then when the model is crashing, and again, you will see information about the log file, where to find them and what to look for them. Sometimes I pick an example that's easy to find what's happening, but often the log files are not that useful, but still it's the place to start to look for information about your crash. Then you will go step by step in this chapter, troubleshooting runtime error. Then the last thing, what we are going to do, the fun example, we are going to try to output a variable that doesn't exist in CAM, and the model will crash. Then the last thing, and then you are bored and you want to go to the next level and modify CSM. Then, for example, let's say that you want to add a variable that doesn't exist in the model. Here I see it's your choice, the red pill or the blue pill, because the blue pill allows you to remain in the matrix. It's a quote from the matrix. And it's a functional computer-generated world, and it's really CSM. And the red pill allows you to escape from the matrix, but with sometimes the painful truth of reality. Because once you start to dig in the Fortran code, sometimes it can be painful, but it's also really fun. Then what you are going to do here, you will go through the source modification, and then you will go step by step until you do the exercise. Then I really recommend that you don't jump right away to the exercise. You read the overview, you read this, and then you do the exercise. And again, this will show you where to do, at which step into the 4 commands of CSM you are doing your source modification. Okay, then this is what you are going to do today. Then now I want to, a few frequent answer question. Then people say, I'm not even finished Monday exercise, what should I do? Then I want to remind you that you should not compare yourself with your neighbor, because People are coming with completely different expertise. We have early graduate students, we have postdoc, we have people that are even further in the career, you have people who have been working on computer for many years. Then don't compare yourself, then this is not a race, and it's better that you try to understand the basic, even if you're still in Monday exercise. It's completely okay, and I will help more the people who are lagging behind, that people who tell me, I want to implant this new parameterization in CSM. It's not the purpose of this week. And you should not be ashamed. This is not, you are doing nothing wrong. And also, you have people that are moving faster because they have experience. What should you do? Then maybe you should start to help your neighbor and try to see. Working with CSM, it's really a teamwork. We are working here to NCAR as a team. I work with all the people that you are seeing in the lab, and it's really a team effort. And you are also learning a lot when you are helping somebody else. Then another question that I had in the lab. Everybody is called, it was on the first day, B1850.basic. I'm a bit confused. And it's true. Then when you look what is called B1850 basic, this one is called my CSM code. But this one here, you have the case directory that's called B1850 basic, you have the run directory that's called B1850 basic, and you have the archive directory that's called B1850 basic. Then what we are really trying to teach you also here is to navigate the maze of CSM and to try to find a lot of this week, it's really to learn how to navigate between this directory and what's inside each directory. Then I did a lot of plot like this, then this one is over here, graph like this, because I'm very visual, but people learn differently, then you have to find what works the best for you. But yeah, you have to figure out where you are. There's some information here to help you. This slide should be on the web after this talk, then I hope it will be, but otherwise call us. But yeah, this is normal. It's very confusing, but after it seems obvious after a little while. The last thing, you are completely confused about the tutorial special queue. What should you do? Then again, there's some information here. On this slide, I didn't update the project number from last year, but there are here information about the tutorial queue that you are using for this week and the account number that you are using for this week. Then there's some more information here. Then this is what I wanted to show you. Then if you have questions, I'm here. If you have questions later, I'm in the lab. And I recommend that you go at your own space and don't be afraid to go. There are no silly questions. Okay? And also, if you find place in the documentation, it's completely unclear and you don't understand, please let us know, because we want to have this documentation to be useful to you, and then people can use this later. Then please let us know, and then we are improving it. Okay. Yeah.
My name is Keith Lindsay. I work here at NCAR. I work with the ocean biogeochemistry component of CESM, studying the carbon cycle and other biogeochemical cycles within the ocean, as well as studying the global carbon cycle as it's coupled between the ocean and the atmosphere and the land. Most of my talk is going to focus on the ocean biogeochemistry. If I go a little slow, there won't be as much time to talk about the coupled carbon cycle, but we'll see if we get to that or not. But the slides are all available online, so if you want to go back and if we don't get to some stuff, you can go back to that later. So the basic outline of what I'm going to talk about is some of the large-scale ocean biogeochemical features that are seen in observations. So this part of it is, it's not modeling. It's what's happening in the real world. What do we see? What are the main properties that we see? And connect it back to the processes, biogeochemical and physical processes that lead to those large-scale patterns that we see in the ocean. And so that will encapsulate the primary processes that are relevant in ocean biogeochemistry that then we capture in models. I'm going to do a bit of a deep dive into one of those processes, which is the modeling of ocean biological productivity. This is the critters that grow in the surface layers and convert inorganic forms of nutrients and carbon into organic forms, their cellular membranes, for instance, and produce oxygen as a byproduct. I'm going to talk about some of the modeling approaches for that particular process. I'm not going to go into detail in the other processes that I will highlight in part 1. Then I'm going to mention some of the ways that we do assessment of the models of the biogeochemistry, and time permitting, get into the global carbon cycle, how the ocean carbon relates to the rest of the system, particularly with our Earth system models. So to start with, here are observations. This is not models. And pointer, this top panel is of a ocean tracer, an ocean constituent called nitrate. That is a nutrient that is used by phytoplankton or living organisms in the ocean. It is used to make DNA. It's part of that the nitrogen in DNA comes from the nitrate that critters consume when they grow. It's part of their cellular membranes as well. All parts of the cellular body is consumed, nitrate is a part of it. And this top panel is showing a distribution of nitrate in a section within the Pacific Ocean. This little offset here is showing where this track is going close to the date line from Antarctica on the left side of this panel up to the Bering Sea on the right side of the panel. So we've got latitude running horizontally and depth running vertically. That's nitrate. And then the bottom panel, which is oxygen along the same track. Oxygen is produced when biological activity happens, and when biological production happens, oxygen is produced. When there's remineralization of organic matter into inorganic forms, that decomposition, oxygen is consumed. So now I'm going to talk about some of the features that we see in these observations. And what these little dots on here are where the actual discrete observations happened that lead to the color coding and the contours in these plots. So this is a pretty densely sampled section of the ocean, so that these features are all well resolved in these observations that I'm describing. Some of the features that I'm mentioning is nitrate in the very surface layers, sort of like low in mid latitude, is low compared to other places in the ocean. And that is because that is where primarily productivity happens and the nutrient gets consumed, and the productivity happens until there's no more nutrient to fuel that productivity. It is a necessary ingredient for biological productivity. You also need light for photosynthesis to happen, and that's the very low part of the food chain where photosynthesis is happening, so that biological productivity is confined to the near surface depths where light is available. So nitrate is consumed there and oxygen is produced. And one thing that we'll see immediately is that it's not a mirror image going on between nitrate and oxygen. And one of the differences between something like nitrate, which is just a dissolved nutrient ions in the water, and oxygen, which are dissolved molecules, is that oxygen exchanges between the ocean and the atmosphere at the sea surface. And that exchange of oxygen between the ocean and the atmosphere depends upon how soluble oxygen atoms are within the seawater. And the solubility of oxygen within seawater is highly dependent upon temperature. Cold water holds more oxygen. You see that there's more oxygen at high latitudes, and warm water holds less oxygen. So this productivity that happens that consumes this nitrate, say at like 20 south here, where you see it's really low, produces oxygen, but that water is very warm, and a lot of that oxygen that is produced is then gassed out into the atmosphere. So that is one of the processes. Air-sea exchange of oxygen is one of the processes leading to the patterns that we see in oxygen contrasting with nitrate. So a lot of times you see inverse relationships between nutrients and oxygen, but not always, because some processes affect one of those and not the other. When the critters consume that nitrate, they go through their life cycle. They might get eaten by higher organisms up the food chain, zooplankton. They might just die, have mortality. And depending upon the mode of their death and also characteristics about the plankton, when they die, some of that organic matter sinks into the water column. Some of it remains suspended near the surface and is remineralized back into organic matter by bacteria near the surface. Some of that is exported to death through gravitational sinking or through large-scale circulation patterns. And then when some of that remineralization of organic matter back into inorganic forms by bacteria, there we go, back to where I want it to be, leads to larger values of nitrate at deeper depths, because this is where along the pathways that the water masses have taken to get to these locations in the North Pacific at these intermediate depths, a lot of respired nutrient has been going on. That organic matter along that pathway is respiring and being remineralized back into the inorganic form, and it's accumulating that inorganic nitrate and consuming oxygen along the way. And that leads to larger values of nitrate in the North Pacific at this 1 kilometer to 2 kilometer depth, and lower values of oxygen. It's not just happening at that location, it's all along the pathway of that water parcel as it's being circulated throughout the ocean. So I think I'm hitting most of the points here. Whoops, I'm doing it again. I'm not used to this. Yeah, I think I'm hitting most of the points there. So that is a nutrient and a dissolved gas, which is produced when biological productivity happens. We include these biogeochemical cycles in our climate model. One of the primary reasons we do that is because it's a climate model, an Earth system model where we care about the climate and we care about atmospheric concentrations of CO2 and how processes within the Earth system impact that. So one of the next slides is showing dissolved inorganic carbon, which you can think about as dissolved carbon dioxide gas within the ocean. It's a little bit more complicated than that because there's some involved chemistry that leads to dissolved CO2 gas, breaks down into other constituents called the carbonate system. I'm not going to go into all the details of the carbonate system. That would blow away my time allotment. So just think of DIC, dissolved inorganic carbon. Just pretend that it's dissolved carbon dioxide gas. We care about carbon dioxide gas in the ocean at DIC because it's really relevant to climate. You might have heard about CO2 and greenhouse gases. Carbon dioxide has some characteristics similar to nutrients. Carbon is required for life forms. When biological productivity happens, carbon is assimilated into the cellular structures of organisms, just like nutrients are. And when the organisms die and their organic matter is remineralized back into an inorganic form, the carbon dioxide is also then, that DIC is created during those processes. So it shares a lot of properties similar to the nutrients in terms, so you have low values near the surface and deeper values in the North Pacific here. So that has some characteristics, patterns very similar to what's going on with the nutrients that I showed in the previous plot. But carbon dioxide also has gas exchange with the atmosphere, like oxygen does. So it has the same property that cold water holds. It has a higher solubility of dissolved CO2 than warm water. And so you end up with large values of DIC, CO2 at high latitudes where there's cold water. And if you were to look at a relationship between DIC and nitrate in these low latitude surface waters, you would see some deviation from a perfect relationship we'd get from biology because of the air-sea exchange that happens with carbon dioxide, with CO2. So carbon, which we really is what we care about, shares both of these properties. And so you have to still get, if you want to do modeling of the carbon cycle, you need to have the processes that are relevant to the productivity and the remineralization and the transport and the vertical redistribution of organic matter in mixing and air-sea gas exchange. All of that comes into play for carbon dioxide, which we care about because of climate. This is a map. It's a bit of a dated map now, because you can see that this is from the year, this is air-sea CO2 flux from the year 2000. So before, the plots were showing just the depth, latitude, characteristics of carbon and a nutrient and oxygen along this transect in the Pacific Ocean. Now this is looking at the surface, the air-sea exchange of CO2 between the ocean and the atmosphere. So you start to see more in the spatial patterns of how all of those processes lead to spatial patterns of CO2 exchange between the ocean and the atmosphere. And some of the processes that are dominant in that would be, for instance, upwelling of cold, carbon-rich waters at low latitude within the Pacific Ocean. This water is being upwelled from the depths, and it is, when it gets to the surface, it is cold and carbon-rich. It gets to the surface, and at these latitudes, it warms up quickly, and it's oversaturated because it's been accumulating carbon dioxide, DIC, along its pathway of circulating through the ocean. So it's oversaturated, and then it warms up even more and becomes even more oversaturated. And that red that you see there is outgassing, because it's oversaturated from the accumulation of inorganic matter, and it's warming. And so you get a big outgassing signal going on at these low latitudes. At intermediate latitudes, we see the opposite is going on, that we're getting subduction of water going on into intermediate water formation regions, and that is taking carbon to depths, and then it is taking up carbon into the ocean. So that's going on at intermediate latitudes in the northern hemisphere and in the southern hemisphere. Farther south, in the closer to the Antarctic coast, or along the Antarctic Circumpolar Current, the ACC, we see outgassing in the ocean dynamics. The pathways of the water parcels there is a bit more involved than the simple models of simple descriptions in what's going on at low latitude. You've got waters coming up from some regions and waters going down in other regions, with the different pathways and different water masses going on in the Southern Ocean. And then another example of where things are going on is like in the North Atlantic, where you have deep water formation, which is taking carbon to depths from that deep water formation. Water cools and takes up carbon and then mixes deep. So you get some hot spots of carbon uptake in the North Atlantic. So all of these processes, the biology and the physics, combine to produce patterns like this. And those are the processes we include in our models. And this is then what gives us an exchange between the ocean and the atmosphere for CO2. When you add anthropogenic increases in atmospheric CO2 above that, that tends to increase the net uptake of carbon into the ocean everywhere. But because of the when you add carbon to the atmosphere, then the seawater tends to be less saturated compared to increased values of CO2 in the atmosphere, and that leads to uptake of carbon in the ocean from the atmosphere. Something that you may or may not have heard about is that of anthropogenic emissions of carbon dioxide, like 30 to 40% of that comes from our cars and factories, in concrete cement production. About 30 to 40% of that dissolves into the ocean into DIC. Makes the ocean more acidic, and critters don't like that. That's another story. So a picture paints 1,000 words, but some people also learn better by seeing the words themselves. So just to really hit home what I've been talking about the last few slides is that the big processes that are governing the distribution of these nutrients, oxygen, and carbon are there's biological productivity in the euphotic zone, which consumes nutrients and inorganic carbon, produces organic matter and oxygen. That organic matter that is created by biological productivity is exported out of the euphotic zone through sinking particles, such detritus, the dead carcasses of those cellular organisms, or calcium carbonate shells, or silica shells for more really beautiful phytoplankton called diatoms. And then they're more mundane things like their poop. And so that leads to stuff that sinks gravitationally through the water column. And some of that export out of the euphotic zone also just happens through circulation and mixing of suspended matter following ocean currents. That organic matter is remineralized back into inorganic forms farther downstream. And this is sort of the reverse of that productivity. It mostly happens through bacterial breakdown of that inorganic matter into inorganic forms, and that consumes oxygen in the process. So it's a bit of the reverse of that top bullet. And then there's this general circulation that is governing these distributions as well. Advective transport and that large-scale circulation, and the impact of lateral and vertical mixing. So the lateral mixing through mesoscale eddies that Gustavo and Peter spoke about this morning, as well as vertical mixing through, it happens near rough topography in the depths of the ocean, as well as near the surface through turbulence. Those also contribute to these global distributions. And lastly, the temperature-dependent air-sea gas exchange governs is a large-scale process for dissolved gases in the ocean. Those are the large-scale processes. There's a whole bunch more processes that can be significant regionally. I'm not going to go into these in any sort of detail, but I'll just highlight what some of them are. One is the atmospheric deposition, the deposition of atmospheric nutrients. And this can be something like the micronutrient iron, which is, it's not something that shows up in your DNA, but it's a crucial micronutrient for biological productivity. It's necessary for biological growth. In the atmospheric deposition plays a large role. Atmospheric deposition of iron does play a significant role in some of that surface productivity. There's also, to a lesser extent, nutrient deposition of nitrate and phosphorus that can be on dust particles that are transported from the terrestrial system to the ocean via the atmosphere. We can get some burial of some matter into the sediments. I talked about that gravitational sinking of particles. Some of those particles do reach the sea floor even when it's in its deepest levels, less so when it's very deep, like 6 kilometers. But some of that matter that hits the sediments is buried there, and then it does not get introduced back into the system until you really reach geological timescales, like millions of years. Where there's large rivers, we have riverine inputs of biogeochemical constituents, carbon and nutrients, particularly downstream of major agricultural systems where nutrients are applied. So like the Mississippi River has a lot of nutrients that come off in that outflow. The Amazon just has an enormous amount of nutrients that come into the Atlantic Ocean because of the large volume of water that's coming there. And large rivers occur all around the world. And they can play a very large role regionally near relatively close to the mouths of those rivers. There's another process that kicks in for the nitrogen cycle called nitrogen fixation, which is sometimes there's dissolved nitrogen gas in the seawater, which is usually not biologically available to organisms because the bonds in an N2 atom are really strong chemically, and most organisms cannot break that down and use that in their cellular membrane. Some organisms can convert that into forms of nitrogen that can be used biologically. And so that can play a large role regionally. It also requires a fair amount of iron to do that. This converts dissolved nitrogen gas into ammonia, which is then usable biologically. And then conversely, there's another process called denitrification, which plays a big role in the nitrogen cycle. Some of that organic decomposition of organic matter, I said that it consumes oxygen. Well, if there's no oxygen available for that decomposition, then there are other bacteria that still do decomposition, and they can use other forms of oxidant-containing material to do that decomposition. And one class of them use nitrate to get the oxygen to fuel that decomposition, and that's known as denitrification. So this is the consumption of nitrate during remineralization when oxygen is low. So that's the big, large-scale processes, and then a brief talk about some of the smaller scale processes. Now I'm going to talk about some of the modeling of productivity in the surface waters. We represent our biogeochemistry models as something called an NPZD model, because I'm sure you haven't heard enough acronyms yet. So we're going to throw more at you. What this stands for is nutrients, phytoplankton, zooplankton, and detritus. And we have different, so in our, whoops, did it again. We have multiple nutrients in our model. I just showed, in the first plot, I just showed nitrate, but there's nitrate, ammonium, phosphate, silicate, iron, etc. All sorts of nutrients that are required for productivity. In this very simple model that I'm showing on the right here with different circles representing different constituents of this model, this model is pretty simple. It just has an ammonium box and a nitrate box for nutrients. Then there's phytoplankton. And in this model here, there's just one type of phytoplankton being represented in this fashion model. There's grazers, the zooplankton that eat the phytoplankton. As she said, this phytoplankton consumes the nutrients. Both of them, then the phytoplankton and the zooplankton then lead to detritus at the end of their life cycle. And then there's also bacteria, which is breaking down the organic matter being formed by that productivity. This is a very simple model, but all of those arrows represent flows of matter from one to another through a different process. And though every arrow is a process that we use, that we represent in our model. And this is a simple model. Here's an even simpler model, but showing some of the equations. This model is just an NPZ model, no D. So in this model, we have equations for phytoplankton, zooplankton, and nutrient. And it has all these terms with all these coefficients, but they all mean something physically. They all are representing different processes in the model. So this first term here is productivity. And there are a lot of terms that contribute to the representation of productivity in the model. There's a light term here, and in some of the coefficients here, E stands for the light incident into the system, because E just means light. It just rolls off the tongue. Here's a nutrient limitation term that shows how that productivity is modulated by the availability of nutrient, and there's some coefficients there. And there's a ideal growth rate factor out front, which then gets modified based upon lack or availability of nutrients in light. There's a grazing term where the phytoplankton are grazed by the zooplankton. And then there's a mortality term where the phytoplankton die. Now the equation for the zooplankton is a bit simpler. There's a mortality term for the zooplankton, and then there's a grazing term for the phytoplankton that gets grazed, gets consumed and ingested into the zooplankton. Now, if you're really keen-eyed, you might notice these terms are not exactly the same, because there's a coefficient out front here called A, which is part of that grazed term is ingested into the zooplankton, and the rest is not. And you can think this is sloppy feeding, that They munch on a phytoplankton, and some of it gets ingested, and some of it slops into the ocean. The remainder of that term shows up down here and goes back into the nutrient pool, and then the mortality terms are mapped into the nutrient pool, and the productivity comes from the nutrient pool. So this is a really, really simple model, but it has just three coupled ordinary differential equations. Everything everything that leaves one pool goes somewhere else, so it conserves mass. That's something I'm highlighting in this last bullet. But there's like a dozen parameters in this really, really simple model. So how do we get those parameters to estimate them for a really simple model? And what we're using in CESM is far more complicated than that. In CESM, we have over 100 free parameters that we need to adjust in our model compared to the dozen in this really, really simple model. So the ways that we estimate these parameters are from laboratory and field experiments, looking at photosynthesis irradiation curves, like expose phytoplankton to different amounts of irradiance, light, and see how their photosynthesis changes. And so that can lead to some of the coefficients in that productivity term. We did the same thing for nutrients to see if you add nutrients in cultures, how much do the phytoplankton respond? We can optimize this against field data and observation, so it's a bit more messy because other things going on out in the open ocean. And sometimes we just use the same values we used in an earlier generation of the model, because redoing everything from scratch every time is too cumbersome and time consuming. Some of these models just have a single type of phytoplankton in it, like NPZD. We have other types where we represent multiple types of phytoplankton in the model. In the real world, there are thousands or perhaps millions of species of phytoplankton. We cannot include all of them in our model. What we do is we sort of represent classes of them in single boxes. It's like all of the diatoms, the ones that make silica shells, we put them in one box. All of them that do nitrogen fixation, though there's many species that do that, we put them in another box. All of them that are that are really small, that thrive in low nutrient, high light situations, we put them in another box. This leads to this concept of plankton functional types. That this is what we use in our model, and in CESM we have 3 functional types. And in CESM3 we're going to have 4 functional types of phytoplankton plus grazers. So there's different types of complexity of these biogeochemistry models. Which one's the best? Which one would you want to use in your model? I'm already running behind, so I'm not going to go into a lot of detail here. But there was a study here that was done by, there it is, Friedrich et al., whoops, who studied different types of complexities of biogeochemical models, a dozen different models with varying types of complexity to evaluate which ones do best with untuned models at 2 sites in the equatorial Pacific and the Arabian Sea, and high values are bad. So she sorted models by complexity, low complexity to the left, high complexity to the right. She tuned the models and showed that if you look at the, just in the equatorial Pacific, one location, the high complexity models do just a little bit better than the low complexity models. So you pay a lot more for those complex models, but if you just run it in the equatorial Pacific, you're not getting much bang for your buck. Then she did an experiment where she tried to tune the models to work at both sites simultaneously. What if you try to use the same model in the equatorial Pacific and the Arabian Sea? Very distinct biogeochemical situations. There you start to see a difference between the models. That the more complex models are doing better than the low complexity models. Then she did another experiment, which is a concept of transferability, where you tune it for one location and then use it in another location. And there the complex models did even better. Why is that relevant? That's relevant because you might have observations to tune your model from just a few sites around the world, but if you put it into a global model like CESM, you want it to work well everywhere. So this says, like in this bottom left panel, that having a model that is tuned to work well everywhere might work well at other places. And so the complexity pays off for global models. And similarly, what if you tune it for present day and you start running the model in a future scenario or from a scenario really deep past? Will your complex model do better or your low complexity model do better? What this says that if you tune your model to work well globally for the present day climate, there's hope that it will do well in other climates. So for a climate model like CESM, where we want to run globally and for future extreme situations or for deep past, there is some benefit for the high complexity model. If all you care about is equatorial Pacific for the present day, you don't need that Mercedes version of model. You can get away with a low complexity model. So a key point from this slide is, what is the best model? It depends on your application. If you want the global model that works for the future and today and the past, you need a more complicated model. If all you care about is a regional setting, the low complexity models are great for you. This is a diagram of CESM. This is a more complicated version of that FASHM model that I showed, that NPZ model. Here we've got, whoops, I did it again. We have multiple phytoplankton of have nitrogen fixers, the diazotrov diatoms. They make beautiful silica shells in small organisms. These also have a component of chlorophyll, which we can observe from space. There's a zooplankton, there's a detritus, and there's a whole suite of inorganic tracers that are required. And all of these arrows are showing the processes that we represent in CESM. This model was originally described in some papers going back to 2004. More recent versions used in CESM2, which you're using in the tutorial, were described in a paper by Matt Long in 2021. The primary features, as that diagram showed, are there multiple nutrients, multiple plankton functional groups, 3 autotrophs, 1 grazer. We have a representation of coccolithophores that make calcite cells, which are really beautiful creatures, and they lead to chalk, but not many people use chalk these days. They're beautiful creatures, though. And they're adding biogeochemistry to the ocean model adds in CESM2 32 tracers. In CESM3, we're going to be using more because we're using 4 autotrophs and 2 grazers, so there's more tracers. And here are some of the additional features going on. Our primary focus is primary productivity. And so we want to know the impact of the biogeochemistry on the carbon cycle. So we do have some features that, because of that focus, we don't do so well in CESM model. The calcification and open ocean of calcium carbonate dissolution are independent of some of the carbonate chemistry. Riverine inputs are prescribed as opposed to coming from the land model. Stuff that's buried in sediments or lost from the system forever. We don't have that really long time scale of geology. We're not treating biogeochemistry in sea ice, and we're focusing on these lower trophic levels. Very quickly, the things we do validate our models with observations from World Ocean Atlas of nutrients, carbonate system from GLODAP, another observational product. Satellite, we compare to chlorophyll to satellite observations. Fluxes are coming from observations of fluxes made by shipboard measurements. More recently also from drones, from gliders that are going around the ocean measuring parts of the carbonate system. And there's observations of iron that we validate our model with. And this is an example of CO2 flux in the model compared to CO2 flux from a observationally constrained neural network. I think I'm going to end up stopping it here. Some of the challenges are coming up with those parameters. In CESM, we have hundreds of parameters. And I'm going to stop it there and not going to get into the coupled carbon cycle because I'm short on time. I rambled on too much about productivity. If those are interest to you, take a chance to look at the slides. And you can see, for instance, more I have a ton of references about the global carbon cycle represented in Earth system models within the CMIP 6. There's much more in the subsequent slides that I'm not going to get to today. So I'll leave it there.
You've mentioned CO2 as an anthropogenic driver. What about, I'm thinking about microplastic. Do you think that might be relevant in this biogeochemical cycle? Because I've heard about a study where they worked on like microplastic changing the grazing behavior of zooplankton and therefore then consuming less phytoplankton. And
I'm not familiar with that study, but that's fascinating.
Okay.
We do not include microplastics in our CESM model. It is certainly becoming a concern globally because microplastics, as I'm sure you've heard, show up everywhere,
yes,
even in the depths of the ocean. I do know of some projects that are working at modeling microplastics just as an inert tracer being transported by ocean currents, getting from the coastal environment out into the open ocean. I was not aware of that being connected to the biological behavior. That's really fascinating. I'm not familiar with that. But no, we don't have that in our model.
Okay, I was just questioning like what, like if there is like a global effect.
Yeah, I'm not familiar with that with that sort of study, so I can't. I could make something up that I just made. That doesn't help anyone.
So, on your NPC model slide, we see a bacteria component of the model. I'm curious where the bacteria was in the model. Where is it the equation, or do we parameterize the microbial processes and stuff like that?
In the fashion model, I think they're explicitly modeling it, the bacterial pool. In CESM, we are not.
Okay.
So we are making assumptions about bacterial abundance that lead to the remineralization. And so we effectively, one of the things we'll do is have like a temperature dependence on that remineralization, which is effectively saying that the bacterial abundance depends strongly on temperature. And so that the effect, we're modeling the effect of the implicit effect of the bacteria through the temperature dependence without explicitly modeling it. So the fashion model had it explicitly. We do not have it explicitly in CESM.
Can I have another quick follow-up question? So I study marine archaea. So I'm curious whether like the newer versions of the ocean models, biogeochemical models will include any of the nitrifiers, ammonia oxidizers, and stuff like that.
In CESM, no, not explicitly. There might be other models out there that do that. I'm not sure. I can only speak for. I'm knowledgeable about our model, less so about. There's a whole sea of models out there. There might be some that are doing that, but I'm not familiar.
In terms of productivity, like in the context of climate change, like marine productivity, do you consider like the gas emissions like DMS from like biological activities at the ocean surface?
That's a great question. In CESM, we do not have that. Some of our collaborators at Department of Energy Labs included a parameterization of that, then coupled DMS emissions to cloud into the microphysics of the atmosphere. We don't have that. In that study that they did never really got its way back into our version of the model. They started with our model, but a whole other can of worms. No, we don't have that here. I've heard people talk about interest in reviving that because of the feedback to the microphysical processes relevant to cloud formation, for instance, which is probably
a quick follow-up, as well as like in addition to the gas like emissions from the ocean primary production or like biological activities, do you consider the aerosol production, like biological aerosol production?
No, we don't have that in our model. We do have aerosol deposition
Yes.
onto the ocean,
Yep.
which is leading to dust and iron relevant for, but we don't have, there is there's a sea salt emission data set that the atmosphere uses for the microphysics, but that is not coupled to the ocean biogeochemistry explicitly.
Yeah, it's just that I know that the organic matter, detritus, it can be aerosolized along with sea salt. So I'm just wondering if that's a process that people consider in terms of like ocean atmosphere interactions.
We don't have it in our model. My guess is that it can play a significant role locally in some environments.
Gotcha.
But we don't have that.
I was wondering, or I kind of wanted to hear about like the interaction between the physical ocean models and this like biogeochemical model. Like, I know that obviously the movement of the water would impact the distribution of nutrients or critters and everything. And like during INSO extremes, there's more like carbon outgassing or like stuff like that. But I was just wondering if like these distributions you get from the biogeochemical model can also be used to assess like how the circulation is working like at the surface with the dynamical model.
The primary, the largest effect of the biogeochemistry in the ocean on the on the physics of the ocean is through chlorophyll. And that is, what that can determine or affect is when you have shortwave light coming into at the surface, the depth at which that light penetrates depends strongly on chlorophyll availability. When you're in a highly productive region with lots of chlorophyll, that shortwave light and the energy associated with it is absorbed closer to the surface. And if you're in a regime with less productivity and less chlorophyll, that light can get deeper. That's one of the biggest effects of biogeochemistry on the ocean is regulation of the depth of the penetration of that shortwave light. There's some other instances where I think there have been some papers about migrating zooplankton can induce vertical mixing just through their movement through the water column. I think the literature is unclear on the effect of that globally, but the light in chlorophyll is a biggie. Sure.
Hi, thanks for the talk. So you said that you use satellite observations for validation of PFTs. So I am curious about that. There are different kinds of satellite observations and each have their own kind of biases. And also they give different kind of PFTs. So how do you reconcile that kind of stuff in your model?
Mostly what we use for the satellites are the chlorophyll itself. We haven't yet really transitioned into vetting our distribution of functional groups via satellites. There certainly are satellite products that can do some separation. There's a new satellite that just went up last year called PACE. It has hyperspectral imaging capabilities that can resolve different functional groups in the ocean. I'm not aware of any work with trying to validate CESM with that. That would be worth doing, with all of the caveats that you're referring to about the complexities of the algorithms going from the radiation measurements. It's a model in itself to go from the radiation to the functional group characteristics, and those have their own caveats.
My experience is that there are variabilities like Copernicus system has got, Copernicus Marine Services has got a system of satellites which give you the kind of PFTs, and we have got MODIS, and we have got from different algorithms which kind of give you PFTs from MODIS, but they don't match always. So that's the kind of situation.
Well, in that, things that don't match applies to some of these even simpler things like the chlorophyll and the productivity inferred from satellites. That is when you've got multiple satellites when you've got a satellite with multiple algorithms that can produce vastly different estimates, seeing the diversity of the observational-based products, that's how I would refer to them, does help put in context a model observation comparison. That if the observations are all over the map, you don't necessarily want to say, hey, I look like that one, so therefore I'm great. Or I don't look like that one, so my model stinks. It does tell you something about the uncertainty in the observationally constrained products. It does inform that comparison. It's still useful it can still be useful to do that comparison, but you need to be informed about the strengths and weaknesses of the satellite product in the algorithms that are underneath it.
In the interest of time, we can take one last question.
Yeah.
I'm wondering if there's been any effort to add kind of proxy system models into CESM so that you could take all of this biogeochemical information along with the like physical ocean model and predict something like what would a sedimentary record of alkenones look like in this location for comparison? Because I know that's kind of up and coming, are these sedimentary proxy system models. And it seems like CESM could produce all the information that would inform those.
That's a great question. I am not aware of efforts to do that with the model we use in CESM, but that could probably be a fruitful avenue to pursue. But I'm not familiar with active work on that. That doesn't mean it's not happening. I just can't I don't know, I'm not familiar with it.
Okay, let's thank Keith again.